Thank you, thank you, thank you. Hello, everyone. Thank you very much for being here today. Whoop, I didn't fall. This is the last day of PyCon UK. This is the last keynote of PyCon UK. I hope you have all enjoyed the past few days as much as I have. We know that we wouldn't have been here, we wouldn't have had so much fun as we had if it wasn't for a number of people. You know who they are the organizing committee and the volunteers, so please, a really big round of applause. So thank you for having us, thank you for being here. Also thank you, Daniele, for the amazing introduction. I would like to take a few moments to also talk a little bit about who I am, what I do, and where I stand within this community. I have a cold, and I'm sorry if I sneeze or cough during this talk. Ben, if you see me and I'm about to sneeze, maybe mute it, that'd be great. But who am I? Well, like Daniele said, I am a PhD student at Cardiff University. Within a few weeks, I'm starting my third year, and there I am based in the Department of Mathematics. And what I study is something that is called game theory. And game theory is all about human interactions. And this is what this logo represents is a logo of an open source package, which is very specific for the type of research that I do. And I will be talking a little bit about game theory and this library itself later on today. I am a fellow of the Software Sustainability Institute. This is an institute based here in the UK. The aim of the institute, very clear. They want to make sure that researchers, such as myself, know about sustainability and reproducibility when it comes to software. And this is not always the case. And what they do is they highlight the importance of these concepts, and they try to make sure that people follow them using best practices. Lastly, PLOS is an academic journal, and PLOS Channels is a web platform. Each channel is designed for a specific community, a research community, and what they're doing is that they want to make sure that when you come and you have a specific interest, you can find resources. I am an editor for the Open Source Toolkit channel. I pretty much write about software. But where do I stand within this community? So I have been using Python for the past 2.5 to 3 years. I have attended PyCon UK 3 years now. I actually gave my first talk here at PyCon UK in a small room nearby, so it's great to be here and keynoting today. I have run workshops. I ran a workshop yesterday with Tanya and Kat, and I'm also a co-organizer of Django Girls for 2 years in a row. A really big shout to Anne, the woman without Django Girls UK would have not been such a big success, and Owen and James. Very successful workshop. This year we had a total of 53 women being introduced to Python and programming. Like Daniele said, and I have been part of organizing PyCon Namibia for 2 years and have attended the conference. Luke gave an amazing talk, and he explained why this conference was so important to the African community and the things that came out of it. For example, PyCon Nigeria, PyCon Ghana, an amazing lightning talk about this year's event, and also PyCon Zimbabwe. Something else that's going on in Zimbabwe is something that is called ZimboPy. And ZimboPy is an organization that aims to teach women in Zimbabwe how to code. The people in charge are amazing people, and they run mentorship events twice a year, and actually I am a virtual coach. I was a virtual coach to the one that took place in August. So this is who I am, and this is where I stand with the community. But what am I here to talk to you about today? Is this. What you're seeing here, it's a pendulum. What is a pendulum? A pendulum is a weight which is attached to a string, which is attached to a stable point. Now we swing the pendulum, it's going to go right and left, and it's going to do that in a periodic manner. Fun fact about the pendulum. At any given point, I can tell you exactly where it's going to be. And I can do that using mathematics that I was taught in high school. You might try to trick me. You might say, okay, I'm going to change the weight a little bit. You might even try to change, the string itself. You might even try to change gravity. No matter what you do, I can tell you exactly how this pendulum is going to behave and exactly where it's going to be. But what happens, something interesting that comes, well, interesting to me, is what happens when we have two of these well-defined rules interacting with each other. And what do I mean by that? Imagine I have a second single pendulum, and I attach it to the end of the first one. I'm going to create something that is called the double pendulum. Please take a moment, think, find a person next to you, and discuss about what is going to happen when I attach two pendulums together. I'm going to wait for a thumbs up, and I'm going to go on. Thumbs up? Thumbs up. And the answer to our question is this. Now, some of you might think, now this is a mess. But this is not a mess. What we're seeing here is chaotic behavior. More importantly, what we are observing is how chaotic behavior emerges by very simply taking this well-defined rule and making it interact with itself. And something that we cannot explain, I have no means using mathematics, logic, to tell you how it's going to behave. Even if you swing it a little bit different, even if you change its weights a little bit different, it's going to have widely different results. So at any given point, I cannot tell you anything about the double pendulum. Now, where I'm getting at is, this kind of complex behavior surrounds the world that we live in. And sometimes we don't understand where this behavior is coming or where it's going. And this is what I'm interested as a researcher, studying these complex behaviors. You might think that I study pendulums. No, I don't. I actually don't even have a pendulum in my office, and it's something I should address at this point. But it's going to be a running example that I'm going to refer back to you, while I'm going to give you other different examples where I study complex behavior. And I'm going to start by a complex system that I observed. So, as a really good PhD student, when I started my PhD, what I had to do was understand what had been done before me. I had to go out there, read the literature, and see what people did before me, what wasn't done, and where I was going to take my field. Now think about this as a programmers, right? When we have an idea, the first thing that we do is we go on Google. Is there a library for what we already want to do? Are there other libraries that we can use to achieve what we want to do? Or do we have to start from scratch? That's what a literature review is to academics. Right? We understand what is out there. So in order to do that, we need to read academic articles. What I did was write a library that collects information on academic articles. This is a library written by me. It's called ACAS. And you can say that, and what you see is that in a few lines of code, I am going to two scientific journals, IEEE and Springer, one preprint server, archive, and what I do is I collect articles that somewhere in the title, the word Python programming language exists. And by doing that, I can collect about 300 different information on articles. Now, in the information that I have gathered, one of the things that I can see is the name of the author. More specifically, the name of the authors. There might be multiple. So I can create this. If at any given point you wrote an academic article about Python programming language, you might be one of those little yellow circles. What these little yellow circles represent is authors. So here's an author. If you wrote with someone else, you have a connection to this author. You have an edge connecting you. And again, you might say, well, this looks a little bit like a mess. But now we can zoom in. So let's say I'm going to zoom in this point. This is what it looks like. So what we're observing is, here's a bunch of people that wrote together, and there's another bunch of people that wrote together. There is one author that is connecting those two teams. So one question you immediately ask is, how important is this person to the network? Are there other people who are more important than this specific person? And how can we tell? Well, we can use mathematics to study how important nodes, how important authors are in this network. Now let's go back to the single pendulum example a little bit. What I'm doing here is, the simple rule is, you can write with people. But then I'm telling you, you can write with someone else, you can write with the same person again, you can write with someone else again and again and again. And this is the complex behavior here. But we can understand it a little bit, and that's what we're going to do now. I'm using a package which is called Network X. Network X is a package for not visualizing networks, so you can argue that this doesn't look great. But to analyze it, actually you can do everything in a few lines of code. What we're seeing here is that we're measuring how important an author is based on how many people that author has written with. And what you're seeing here is like, they're pretty much all the same, right? None of them is more important than the other. They all pretty much wrote with the same amount of people. Other measures that we can extract more information from? Yes. The second measure that we're seeing here is something that is called Betweenness Centrality. I would like you to imagine that I am here, I am trying to get to that person there with the red t-shirt. In order for me to get to that person, there is a shortest path that I can take. If we were to find the shortest path between any of you to any other person in the room, we'll just end up with a bunch of shorter paths. There are some people that would appear more frequently in those shortest paths. And those people are the people that are important to our network, are the people that if I have to get to your work, if I have to write with you, I need to go through them. And these are the top influencers that we're seeing in the Python programming network. Any fun facts about the top 10 list? Apart from that, is that there are actually no women in the top 10 authors. But let's go a little bit back in our example. All I tell you to do, your simple rule was that you can write with someone. If you tell me that I can write with someone, I'm more likely to write with someone who's more like me. So there is no surprise that what we end up with is just a homogeneous set of authors. Can we change the rules a little bit? What if we said you can write with someone and diversity is a little bit important? The results could be widely different. Can I tell you this? Can I show you this? The answer is no. And that is because all I'm doing in this example is I am observing a world that has already been done. But there are other situations that I can set the rules of the game. And this is what I do as a game theorist. It's all about setting the rules. I'm going to talk to you about two examples. And the first example I'm going to start with is actually my PhD thesis. And my PhD thesis is all about the emergence of cooperation. In 1860s, Charles Darwin wrote a book, The Origin of the Species. What Darwin told us there was like, if you want to be dominant, you want to be the best in your population, you have to be the fittest. But there was something that Darwin himself couldn't explain. It was something he was observing, which is something that we can observe today, that we don't hate each other. We're actually nice to each other. We don't go around punching each other. But why? Why is that? And is that just for human communities? Are we smart? No, actually, our cells behave the same way. Animals behave the same way. And I'm going to give you an example using this little fellow. This little fellow is an animal called a vampire bat. Now, as the name assumes, vampire bats feed on blood. No human blood, animal blood. So the way they do it, we have a group of vampire bats, which are called a colony. So we have a colony, and the colony goes out hunting in the night. They collect the blood, and they come back to the cave. Now, there are some people, there are some bats, that went out there, and they were unsuccessful in their hunt. They came back with no blood. What's very interesting about the animal is that if it does not feed for 2 or 3 days, it can actually starve to death. So now the bats in the colony need to make a decision. If I have food, am I going to share my food with the other bats of the colony? But remember, if I share my food, it means that I might have less. It could lead to death for the vampire bats. But no, actually what we can observe is that the animals do share their food with them, between them. And not just with family members, with other members as well. More specifically, if you ever share your food with a vampire bat, they will remember. And they will remember to share their food with you as well. So can we model this behavior? Can we set the rules for this behavior? Yes, we can. So assume we have 2 vampire bats, and assume they both keep the fish closed. They do not share food. We can say that they're going to be punished, because at some point, one of them will starve. If they both share the food, if they both open the fist, we reward them. Yes, you're going to get food. You're going to share the food. You're going to leave the next day. But what happens is that if you're sharing your food with me, I have a temptation to cheat. I have a temptation to not share my food with you, because then I'm just going to end up with more food. And these little rules that you're seeing here is actually a game which is called the Prisoner's Dilemma. The Prisoner's Dilemma is a very well-studied game, and one of the biggest work was done back in the 1980s. A man called Robert Axelrod decided to study the game using computer tournaments. What he said was like, okay, instead of having humans, instead of having bats playing the game, what we're going to do is you're going to come up, you're going to write a strategy written in computer code. They're going to choose to share or not, to be nice or not, for 200 turns. The strategy with the highest average, with the highest mean, wins. When Axelrod did that, 13 people participated. And the strategy that won was a strategy called tit for tat. Now, tit for tat is a strategy that starts off by being nice, it shares food, and then it just copies what the opponent did. Axelrod decided to run a second tournament, and now this time he had 64 participants. And once again, tit for tat won. Tit for tat was a nice strategy. So what Axelrod showed us, he just gave us more proof that, yes, cooperation emerged. What he actually did, he developed a really well-structured manner of studying the emergence of cooperation. And this is exactly what I do today. Is there a library to do that? Of course there is. Fun fact, it's called Axelrod. So what you're seeing here is, by using the library called Axelrod, I can create a list of strategies. So I can create a list of a player called Cooperator. It's a bat that always shares its food. A defector, a bat that is never going to share its food. And I can play their interaction out for 5 turns. And what you're seeing here is I'm getting CD, CD, CD for 5 times. Famous strategies from the literature are in the library. Yes, for example, there's tit for tat. And what we can see that tit for tat against defector, it starts by being nice. But then it's just going to copy what the opponent did, and the opponent just defected. So they're going to defect all the way through. Is tit for tat the only strategy well-known in the literature? The answer to that is no. There are many well-studied strategies there, and the library actually has 235 strategies implemented. Some of them have parameters, so you can argue that by using different parameter sets, I can have an infinite number of strategies. So my PhD is all about studying behaviors. More specifically, this image summarized my PhD, which is, I want to find what makes a bat awesome. What a bat needs to do in order to be dominant. I'm doing this using three different approaches, 3 chapters. The first one is, I'm going to look down to a specific bat, and I'm going to tell it mathematically what is the best thing that it can do against another bat in order to be dominant. The second approach is, I'm going to create a bunch of colonies. I'm going to go to different caves, create a bunch of colonies, see how the best bats are doing, how they are behaving, but I'm not going to do it on my own. I'm going to set a robot, a machine learning techniques, in order to understand what makes a bat good. The final approach is that, you know what, I'm going to take a machine and I'm going to tell it, you know what, now be an awesome bat. Be the best bat that you can be. So these are the 3 different approaches. So let's look at them. So what did I mean when I say we can mathematically write down how bats must behave? So we're looking at a constrained bat. We're looking at bats that don't remember exactly what happened 2 days ago. They only remember what happened yesterday. They have a small memory. If we consider there are 2 bats that they only remember what happened yesterday, then there are 4 things that could have happened. They both share their food. They both did not share their food. Or one of them did share their food and the other one didn't. What you're seeing here is something that is called the Markov Chains, which has 4 states. And they're given probabilities that our bats are going to move from one state to the other. So we can actually write down how this bat is going to behave by using a vector of 4 probabilities, which are, once you're here, you have a P1 probability to just share your food again. So by doing this, I can write down exactly what my right bat needs to do in order to be dominant to the left bat. sorry. The equations, I studied the equations using a package which is called SymPy. SymPy is about manipulating symbolic mathematics. So I write down exactly what my bats need to do, and then I can use scikit-optimize. And I do that in order to identify the exact values of P1, P2, P3, and P4. What you're seeing here is, well, I can't draw a 4-dimensional space yet, so I'm just plotting a constrained version of the problem where we only have P1 and P2. And that is because P1 can sometimes, if we constrain it, P1 can equal to P3 and P2 can equal to P4. And by doing that, I know exactly how you should behave when you're playing against another bat. So if we go back a little bit to the pendulum example, what I have done here, I've said, okay, for a specific, very constrained version, and after a lot of hard work, what I can do is write down the mathematical equations of how the double pendulum is going to behave. Well, let's look a little bit at the second approach. What do I mean I created different colonies? So we have a set of 235 behaviors. What I can say is I can create colonies of different sizes. There are colonies with 3 bats, there are colonies with 100 bats. Each bat behaves in a different manner. But each colony has a bat that is doing a little bit better. And what do I mean by a little bit better? Maybe it takes more food at the end of the day. I can use machine learning techniques in order to understand what makes those bats the best in the colony. When I started reading a little bit about machine learning, I came across the book called Python Machine Learning Edition 2. I highly recommend it as a reference if you want to start somewhere with Python and machine learning. And one of our results can be summarizing using this plot. What you're seeing here is the blue bar corresponds to the bats that were the best in the colony. The orange bar corresponds to the bats that were the nicest in the colony. So if I had, in a sentence, to tell my bat what it has to do in order to be awesome, it would be find the people in your colony that are the nicest, and then cooperate 0.7 times that they did. So if we go back to the double pendulum example, let's say, what makes a double pendulum better than another double pendulum? It swings higher. I created a bunch of them, and in order to understand what makes it better, what makes it go higher, I sent a machine to check each stable point, its weight, its string, and identified what were the things that made it go higher. But let's talk a little bit about the last approach. And the last approach is all about training a structure to be awesome. Is this the first time this is done? And what do I mean by training? So this has been done before. And actually, this is a picture from one of the works that I have done. And 2 of my co-authors are actually in the room, Vincent and Owen. What you're seeing here, it's a finite state machine. So this is the brain of a bat. What do I mean by training? It means that I can use reinforcement learning in order to change these little arrows. You can argue that all this time I've been talking to you about simple rules and how we can explain them and how then they emerge into something complex. But the rule I'm giving you here is not interpretable. You can't interpret it with a sentence. What's very interesting about this specific strategy is that we trained it using reinforcement learning. And it actually has a very neat feature. What it does is if you have a colony that is behaving exactly by this rule, if another bat from another colony walks in the cave, they will know. They have a mean of understanding that you're not one of them. They have a handshake. They have a mechanism of recognizing each other. I know you can't really see it, but what we do is, if they go from 1 to 8 to state 5, then they end up to state 4. And they're just in a state that they're both being nice to each other over and over and over again. So this is what a complex structure looks like. And when I talk about training, it's all about generating a bunch of data and let the machine learn on its own. So what I'm going to do is use recurrent neural networks to train a bat. What I have done so far is I am creating the food for the bat. So recurrent networks take sequences. So I can use Actrod in order to create a bunch of sequences. I'm not taking any random sequences. I'm actually using evolutionary algorithm in order to generate really good sequences, which are the food that then I'm going to give to the neural network. So the data are currently running. I'm going on holidays on Thursday. So when I'm coming back, the point is to take some libraries that already exist out there, for example, TensorFlow and Keras, and give them the data and train the machine. So let's go again a little bit back to our pendulum example. Now what we're doing, instead of generating a bunch of pendulum, is I'm generating one. For each given point, for the weight, for the string, for the gravity, I'm taking a bunch of data, and I'm trying to identify what is the best thing that can happen for that given point. So what? Now I think some of you actually think that I study bats in my office, and no, unfortunately I don't. I think Charles Darwin himself, when he observed the emergence of corporations, he didn't look at bats. He maybe did, I am not sure. But what happens is that this behavior is not just in bats. It's in our world as well, it's in the human society. We are nice to each other. But being nice doesn't always pay off. My job is all about identifying when does being nice can be evolutionarily beneficial to you. The last example I would like to talk to you about is rhinos. And at this point, I think you believe I love animals, and I do. So rhinos are wonderful animals, and their name comes from two Greek words, rhinos, and kerato. If I say kerato, do you spell it in Latin or in Greek? Latin. You would have blown my mind. So the name of the animal comes from the two Greek words, rhinos and kerato. The wonderful animal, unfortunately, because of the horn, they have value in the black market. So people kill the animal and they take the horn. Now the population is quite small, so all of the rhinos out there today, they live in protected areas. The people who are in charge of these protected areas are called wildlife managers. Now the wildlife managers need to make some decisions how they're going to save the animal. And one very common one is devaluating the horn. And actually the most common devaluation method is removing it. What do I mean by that? I know it sounds a little bit horrible, but remember, they're the good guys. They put the animal to sleep, they put a little blanket over the animal's eyes, and then they remove the horn. Now, things about dehorning is, number one, no matter what you do, there will still be some horn left on the animal, because, well, it's its skin. Number two, the horn grows back, slowly, but it does. So people that kill the animal, they're called poachers, we can say that they behave in two different manners. They can either be selective, and selective are the poachers that say, if a rhino does not have a full horn, it does not pay me to kill it, because it takes time, there's a high risk of me getting caught. So for me, killing a dehorned rhino the gain is not enough. But then there are other poachers that are going to be indiscriminate. So no matter what you do, they're going to kill the animal anyway, because even taking those little crumbs that are left on the animal can make a big difference to them. What's quite interesting, and where we come in is studying the behavior of the population of poachers. What happens when these little guys interact with each other? What we do is we use something called evolutionary game theory. And the idea is, if you have a room where everyone is being indiscriminate, and someone comes up and is like, hey, maybe we should be selective. And we're all like, yeah, you know what, you're right, maybe that's what we should do. Then being selective is evolutionary stable. It's taking over us. But if this little person comes in and is like, hey, maybe we should be selective, and we're like, no, we're doing great. Then being indiscriminate is evolutionary stable. Why these concepts are important? And they're important to the wildlife managers, because if they know how the population is going to behave, then they can change the ways that they're trying to secure the animal. They could, instead of dehorning, maybe put money on security. And our results can be summarized very nicely from this picture. And I'm going to walk you through this picture. This picture illustrates 6 different examples, 6 different worlds. 6 worlds where the gravity is different, the weights of the cell are different, the strings of the pendulums are different. What you're seeing here, for example, is that in one, H, is the value of the horn is 50, but here is 192. So selling horn brings you more money. Another example is there, R is 0.6, and R is the number of rhinos that are being devalued in a world, where here is 0.2, so less rhinos are being devalued. What we're observing is how the population shifts. So in these examples, no matter where we choose, no matter how many selective people were in the room, we're going to take over the population. And what we're seeing here is X is the number of selective people and how it changes. And in these examples, being selective takes over. So me dehorning in this example makes sense. But then there are other worlds that this doesn't happen. For example, here, no matter where we start, we're all going to end up being indiscriminate poachers. And here we have a case that there's a mixed population. Why, again, this is important to a wildlife manager? Because if they know in which of these scenarios they are, then they can choose what they're going to do and where they're going to put money. So as mathematicians, we're trying to give you a model that you can secure the life of the animal. But from a microscopic level to them, no, dehorning makes sense, right? Dehorning means there's less value, so they're not going to kill my animal. But what they do not understand is the complex behavior that emerges. And are there any other questions out there that we think that we understand the question, but we do not see the immediate results? Why does Python have a crash? Like Daniele said, what if only 5 people are using it? Maybe then the cost and the ticket these 5 people buy is not enough to cover the cost. But what happens if those 5 people do not come? What happens if those 5 diverse people do not come? What if the things that we're going to bring to the table are not there anymore? Then we might just end up with a homogeneous community. Why does writing a single line of documentation matter? My library is great. I have tests. Arguably, if you're fluent in Python, you can go open my code and you'll magically know how you have to use my library. But again, what happens about the 5 people that you're excluding? What about the things that these people could bring in your community? How they can make your community expand. And we know that successful packages out there have big communities because it's that make them sustainable. Why having an avocado makes a difference? Avocado is great. It's a fruit, and you can argue that I'm eating fruits instead of meat, and I know the meat is not sustainable. Actually, the high demand of avocado in the past years has affected local communities, and we do not know about it. For example, a village in Kili, what they said is, no, farmers take our water away in order to farm their crops, or they cut our trees down in order to expand. So there are little actions that we do every day that we do not understand exactly the consequences. And that's what I would like to leave you off with. If I had to leave you with one thing today is, what did I do today? Well, hopefully I was here for a half an hour and so, and what I did was giving you different examples of how I can rigorously show you that small actions matter, and they make a difference that me and you might not be able to understand today. So they should not be taken for granted. And thank you very much for your time.
Thank you very much, Nikoleta, especially with your cold.
I didn't sneeze, which was good. This is good.
So, Nikoleta would like to have some questions from the audience. And if I may start with one, because I've got one that's burning in my mind. So, you've addressed the question, you've shown that a smile, or the line of code, or the small change can make the difference. But I also want to know, is there some way I can tell what difference it will make? How will I find out about what things I introduce or new behaviors I introduce, what will be successful and what will not? And that's what we really need, I feel.
I know, but then what you're asking me to do is unfortunately tell you how the world is going to behave. And if I knew that as a game theorist, I probably wouldn't be here. Unfortunately, that's something that we do not know. The way people are going to behave, we cannot immediately understand the results. What we can know is once we've played the game out, that we've seen the results, we can study where did this come from? What were the things that made this world behave the way it did? And maybe if we understand those concepts, then maybe we can change the other worlds the way we want. But forecasting the consequences that human actions are going to have, no, unfortunately, I cannot do that. Yes.
how are you selecting the questions that you are going to be studying?
Throughout my research. No, so the three examples that I gave you today, the first one, it came as a natural question. It just came when I started collecting all this data from articles. I was like, oh, what can I do with it? And is it things that I can understand? So that kind of just came. There are other things like the emergence of behavior that it was introduced to me by my supervisor, but he was like, would you like to study this? Because this is what happens. And I was, I was fascinated by the question. I was like, yes, this is what I want to study. And then again, the Rhino project came. One of our co-authors, Tamsin Lee, she did an amazing poster back in 2016, 17, I'm not sure, sorry. And there she showed her work to us, and we picked it up and was like, oh, we can do evolutionary game theory to do some study there with rhinos. And she was fascinated, and I just took the project from there. So.
Yep.
Sorry.
It's a great talk, Nico. Thank you. Yeah, I have a question. Like, you use non-cooperative game theory to model the situation there for the collaboration of the group. Like, in non-cooperative game theory, it makes a few assumptions, including it have the assumption that each person or maybe each animal will behave for its own benefit, and it normally interact one-to-one with another individual. Have you ever tried the cooperative game theory to model the situation of the collaboration in the group, where like the interaction normally in like group setting with more than like two individuals, and then in that situation it would be a bit different?
Can you repeat your exact question again? Sorry, I can't hear very well.
Yeah. So have you tried to use cooperative game theory instead of non-cooperative to model that situation? Thank you.
Thank you. Thank you very much. No, I have not. I've only used, so I just studied the Prisoner's Dilemma, which is a non-cooperative game. And no, I have not expanded my research to cooperative games. But thank you very much for that. I'll definitely have a look. Definitely have a look.
Hi. Yeah, I'm just curious about how does validation work in this type of research, because it seems to me like you constrain certain things to basically, it doesn't quite correspond to reality, and therefore how can you validate that what you're presenting is correct?
No, several examples. So the Prisoner's Dilemma, actually the study that was done by Axelrod and the tit-for-tat behavior that emerged from it, we could validate it by then observing nature. So there's a really nice paper that actually observes bats, not the way I did, and they showed that actually the tit-for-tat behaviors, the fact that they remember that you were nice to them yesterday, is actually, proof that yes, tit-for-tat actually works, and we can see the network and animals use it. The rhinos, it would be great if we could collect some data about what happens in the local communities. Unfortunately, this is not exactly easy. It's a very settled manner in the local communities. And again, we're talking about black market, so there's a risk there. So we have not been able to collect data yet, but then we could arguably have the data and see if how the world is behaving corresponds to our mathematical models. Yes.
We might describe education as a force for disseminating good things into groups of humans. Is there a way of modelling education or kind of encouragement in game theory?
Encouraging people to be nice. Usually when we do a tournament where people play the Prisoner's Dilemma, we have seen that the groups that win actually defect against each other. So I would love to tell you that you can use the Prisoner's Dilemma to show how people should be nice. No, but again, using game theories, we can use games, and maybe they won't exactly understand on the day that maybe cooperating is the best thing that we can do. But if we just talk a little bit about it, if we just introduce these concepts to them, it can make a difference tomorrow that we do not know about it. So just introducing the fact that, you're all defected, but when you're playing a simple game, and yes, you won, though you defected, but what would have happened if you all cooperated? You would have had such a better output. So just maybe introducing these concepts to them, using simple games, might be an answer.
Yeah. So, sorry, this might be a repeat of the previous question. When you've got a community or a system, how do you determine, how can you measure where it is, get a picture of where it is in the space of possibilities? So you mentioned the difficulty of measuring where the rhino situation is in the space of possibilities, and then any general methods or statements you can make about that.
So for the behavior of the poachers, the way that how they behave, we set the rules for each poacher. If you behave this way, you have this gain. If you behave this way, you have this cost. And then using how much do you get from your interaction with other people, we solve differential equations to pretty much see how the system is going to evolve, if that's your question.
My question is, with the system out in the world, not necessarily for rhinos, how can you get a sense as to what the values of those parameters are, if you like?
Oh, of course. No, so we make no assumptions for our values. Like, again, we could see some of the data if they're out there, but we have everything parameterized because we don't want to make any assumptions of what the value is or what the cost is. So then you can just use we run a parameter sweep when 100 of scenarios are actually created with different values. Well, we know that the gain is higher than the cost in some cases, but no. We make no assumptions at the beginning. The way we make our model, everything is parameterized, and then we just use a big sweep to generate a bunch of data. Yeah, that's great.
Thank you very much. It was an amazing talk. How is the system affected by a single irrational actor?
We can actually model irrational behavior. So some of the 235 strategies in there are irrational. So how the system is affected, it depends on the number of irrational people you have, or who else is in the room. So I can't give you one right answer, but I can tell you that we have means of studying this, if that makes sense. Yeah. Thank you.
So you spoke about interactions on an individual inside a community basis. Yeah. I was wondering if you had sort of a model for a community interacting with another communities?
No. I'm trying to see if the answer is no. No, but there is definitely something that we would like to look at, and we can use this using network theory. And for example, for our poachers examples, we can say that we have two communities, and some poachers, and that's something actually we're doing now, we're modeling the behavior that you can leave one community. So after modeling the behavior that you can leave one community, we can introduce another community and say what happens when you jump from one to the other. And then we can study that exact interaction that you're asking. Look forward to it.
Any more questions from our audience? I have a small question. If we're political scientists or historians, we might want to understand why it is that groups of people behaved as they did in cases, for example, in genocides, as occurred in Europe during the war, in the Balkans, in the end of the last century, in Rwanda. And different people behaved in very different ways, and whole communities behaved in ways that seem to have patterns that repeat throughout history, some behaving in very noble ways and some behaving in very appalling ways. And in the case of the poachers and the rhinos, you're dealing with parameters that have numerical value. But it seems to me that if we're dealing with human people in those circumstances, maybe we're dealing with qualitative factors rather than just quantitative ones. Is it possible to model those, or is that too complex?
So our model takes into account a parameter, and what we believe that this parameter represents is what happens if the local community tries to put more money into education, try to put money on laws, like enforcing laws that make sure that people understand the importance of animals in our ecosystem. So we do have a parameter, and we do say that the interpretation of it is some of the things that Daniela spoke about making people know that they can live with wildlife and things like that. So we do take it into consideration, that one force that we maybe doesn't have an exact numerical value, if that makes sense.
Thank you very much for your talk.
I'm not sure where I'm looking. Sorry. Sorry, yes.
Thank you very much for your talk. So in a world where we can predict everything, basically.
Hopefully. Yeah.
So would not people be able to use it for evil? And would we then be able to predict that they would be using it for evil as well?
I never thought about a world that we can know exactly where everything is going to behave the way that we know everything. I found that quite boring, so I never gave it a really big thought. I'm not sure. What we could do is, like, here's a world, a well-defined world, and we know how everyone is behaving the way it does. Why? Where does this come from? If we're people, if it's a big loop, I am not sure. I'm not sure.
Hi, thanks again for the great talk. If we kind of believe that generally cooperating is kind of good for everyone, is there one thing we can take away from this? Ways that we can set the parameters of our community to encourage cooperation and make it more likely to be the kind of the thing that people land on?
Yeah, so Luke gave a great talk yesterday about maybe volunteer for 1 or 2 days and you do not know the outcome. There are ways of encouraging behavior like this. We do here. The fact that we have a code of conduct, the fact we respect each other. So there are ways of, telling people, no, being nice to each other is nice, and it pays off. I think this community might not have so much to learn about this because you're already a really good and welcoming community and a cooperative community that others are not. But little things that we see within the Python community, I think are great.
Maybe one last question then, unless there's anyone else. For those of us whose mathematics hasn't progressed beyond high school mathematics, all these programs you've shown look completely fascinating. Is there an easy way in for those of us who are less sophisticated to gain some use or maybe even create some value from them?
So the way we write and the way we do our research is, number one, everything is open source. And every time we have a little paper, like the Rhino paper, our code is there, our code is documented, our code is tested. And then we have a notebook as well. And the idea of the notebook is that if you're not fluent with mathematics and you want to read and understand the paper, the notebook is going to literally walk you through the mathematics behind it. There are plots to understand how the functions behave, if we change one parameter, if it goes up and down. So we're trying to do our research in a manner that everything is out there, and we do not make any assumptions. We want to promote our research, right? We don't want to make our research intimidating. So we make sure that, no, if you're actually interested, you don't need to have a PhD in mathematics. And you'll have programming skills, which is pretty much what you need.
Thank you. Okay. I think that we've exhausted our audience for questions.
Thank you very much.
Thank you very much, Nikoleta. That was really fascinating.
Thank you very much.
Happy to talk to people afterwards.
Yes, of course.